Advanced Higher Physics, Electromagnetism, Magnetic Fields. Magnetic Fields, revision from Unit 2. A magnetic field is a region in which a moving charge experiences a force. We already met this in Unit 2 when we looked at particles from space, when charged particles enters the Earth's magnetic field, and that's where we see effects such as the northern lights. The equation that we used for the force on a charged particle entering a magnetic field is F is equal to QVB, and this appears on the relationship sheet. Within this equation, F is the force on the charged particle due to the magnetic field measured in newtons. Q is the magnitude of the charge moving within the field measured in coulombs, and B is the magnetic induction measured in Teslas. We now need to look at this effect of placing a current-carrying conductor in a uniform magnetic field. So as opposed to just putting a single point charge within a magnetic field, we need to consider what the force is going to be on a conductor such as a wire placed within a magnetic field. Please, though, remember that a force will only be put onto a charge or a current-carrying conductor if the charges are moving. If the charge is static, then there'll be no force whatsoever. A current in a conductor we can consider as a flow of negative charges. So we're using the right-hand rule here from higher. These moving charges will all experience the same force as they move through the conductor, which means that there will be a uniform force across the whole length of the conductor within the magnetic field. Forces on a current-carrying conductor. So we know that current is the rate of flow of charge, and this is defined by the relationship I is equal to Q over T, or more commonly written as Q is equal to IT. The charges within the conductor will be moving at a speed, and the speed we know is V is equal to D over T. In terms of a current-carrying conductor, such as a wire, D is going to be the length of the wire. We can change the relationship for a single moving charge that we had before, F equals QVB, for a charge moving perpendicular to a magnetic field, to a relationship for a current carrying a conductor of a length placed within a magnetic field perpendicular. So, previously in higher, we considered a moving charge perpendicular to the magnetic field. Now we're considering a current carrying conductor moving perpendicular to the magnetic field. That is, cutting across it. So if we consider our magnetic field like this, the crosses mean that the field is going into the page. We're considering a current carrying conductor across that field. So at right angles, at 90 degrees. The equation we have is F equals QVB, and what we're doing is we're substituting in our equations for charge and for velocity into these equations. So IT replaces the Q, L over T replaces the V, as in D over T is L over T, and multiply that by the magnetic field strength. And this goes on to form the equation F equals ILB. So this is the equation when we are perpendicular to the magnetic field. That is at 90 degrees to the field. And that's going to become important later on. So let's consider a conductor in a magnetic field. This relationship can be extended to include a conductor placed at any angle in a uniform magnetic field. Remember, F is equal to ILB because we're at 90 degrees to the field. That is, theta is equal to 90 degrees. The actual relationship, as it appears on the relationship sheet, is F equals ILB sine theta. And obviously we can see that sine of theta is equal to 1 when theta is equal to 90 degrees. This is a relationship on the relationship sheet, but it's useful to remember F equals ILB when we're dealing at right angles, as this is pretty common within questions. So we can use the same right-hand rule which we used in higher in order to determine the direction of the force on the conductor. In the case of the example here, we can see that the wire will move upwards. So use the right-hand rule just now. Have a look at the diagram. Remember, your first finger is the direction of the field. Your second middle finger is the direction of the current, and your thumb is the motion or the force. You align your first finger with the field. Your middle finger is moving towards you because that's the direction of the EMF we can see from the arrow within the diagram. And therefore, our motion is up. But remember, that force is acting all the way along that wire. So the whole wire within the magnetic field are going to experience a force. So definition of the Tesla, the unit of magnetic induction. So we should know from Unit 2 that the Tesla, T, is the unit used for magnetic induction. 1 Tesla is defined as the magnetic induction that would produce a force of 1 Newton on a current carrying conductor of length 1 meter, carrying a current of 1 ampere placed perpendicular to the magnetic field. And you need to be able to remember this and quote that. So let's put a star. You should also be able to say where this comes from, and that comes from our equation F equals ILB sine theta. Remembering that at perpendicular to the magnetic field, sine theta becomes 1, and so we can rearrange this in order to find B is equal to F over 1L. So if the force is 1 Newton, the current is 1 ampere, the length is 1 meter, we can say 1 Tesla is 1 Newton per ampere per meter. So this is an alternative unit for magnetic induction. Another interesting thing we can note here is that by rearranging the equation in this way to B is equal to F over IL, we can then talk about the proportionalities of the different factors. So that is, we can say that the magnetic induction is directly proportional to the force which is experienced, or vice versa. The force experienced on a current carrying wire is directly proportional to the size of the magnetic induction. We can also say that the magnetic induction is inversely proportional to current and inversely proportional to the length of the wire. So as the length of the wire increases, the magnetic induction decreases. As the current increases, the magnetic induction also decreases. At higher, you had to explain experiments used to prove certain constants. At advanced higher, you need to do the same thing. In advanced higher, you should be able to describe an experiment in order to establish the relationship between current and force on a conductor placed in a uniform magnetic field. Here's our experimental setup. We can see that we have a pair of permanent fixed magnets on top of a Newton balance, and there's a wire in between. One thing to note is the direction of the magnetic field, which should be north to south. And so we can see our current carrying wire has been placed at 90 degrees to the magnetic field. So a piece of stiff copper wire is placed between the 2 permanent magnets, which are sitting on the electronic balance. When a current is passed through the wire, the conductor experiences a force upwards. Have a think why. Why does the current passing through the wire mean the conductor experiences a force upwards? Pause the video for a minute. Use the right hand rule. Align your first finger with the field, your second finger with the direction of the current. Remember, that's negative charge, so that's coming from here. and then prove that the force is moving upwards. Did you get it? Hopefully so. Because there is a force acting on the wire moving upwards, there is an equal and opposite force on the magnets downwards. That's due to Newton's third law. Every action force has an equal and opposite reaction force. The downwards force experienced by the magnets can be measured with the Newton balance, and therefore we can measure the force experienced by the conductor within the magnetic field. The current is also measured on the ammeter, and a graph can be drawn of force against current. The gradient of the graph will be F over I, just like the gradient of a VI graph is V over I, thus giving the resistance. That gradient and the measured length of the conductor in the field will allow us to determine the size of the magnetic field. Here are a set of example results. We have several currents in regular steps, and we have readings on the Newton balance. For simplicity in drawing the graph, we've made the units times 10 to the negative 3 newtons. The length of the wire is measured to be 53 millimeters. That's not a standard unit of length, so at some point we're going to have to convert that to meters. We could draw this graph, or we could put it into Excel and determine a graph, and from this we can determine the gradient. In this case, 1.74. Remember, the gradient is force over current, and our rearranged equation for F equals ILB sine theta becomes B is equal to F over IL, because theta is equal to 90. So let me put that step in there for you. So F is equal to ILB sine theta. Because theta is equal to 90 degrees, we're at perpendicular to the magnetic field. That just becomes F equals ILB, which then rearranges to B is equal to F over IL. F over I here is our gradient. So we can say our gradient of 1.74, remembering, is times 10 to the negative 3. 1.74 times 10 to the negative 3 multiplied by 1 over the length of the wire, which we've converted into meters, times 10 to the negative 3, gives us a value for the magnetic induction as 33 times 10 to the negative 3 Tesla. So this is a fairly common question where you're asked to determine the size of the magnetic field. However, the magnetic induction is only one part. We could do a similar experiment and we could work out other things. We could determine what the force is going to be if we were to change the length of the wire, if we were to increase the current. You could be asked, what happens if we change the direction of the current? Obviously, the forces are going to go in different directions. Just of interest, we have the electric motor. Now, the electric motor you were introduced to within third year, and it's not really done anymore once you get past your third year and fourth level physics. However, we can combine what we know about our rotational mechanics and what we know about magnetic induction to give us a little bit more detail into the motor. So current flows up one side of the coil, as we can see from the supply. And then this produces a force on one side and a downwards force on the other side. So the current flowing in this direction is going to create a force. Is that upwards or downwards? Have a think. Remember, our magnetic field is going from north to south. Pause the video for a moment. Use the right-hand rule. You should see that the force is acting upwards because the current flow is going in one direction, and then downwards because the current flow is going in the opposite direction. Have a shot yourself. Now, where it can be confusing with diagram and questions like this is the direction of the field, the current. Now remember, here is our negative terminal, So our current is acting in this direction. Current's going from the bottom to the top when it's in the North Pole, but then as it moves around, it's then going in the opposite direction when it gets to the South Pole, which means we have an upwards force on one side, a downwards force on the other side. And this force causes us to rotate. Now, rotating force, remember, is torque. So we have a torque on each side of the coil, making it rotate, and the split ring commutator allows the current always to flow in the same way in the coil as it rotates, so it maintains a constant, in this case, clockwise rotation. Magnetic induction around a conductor. A magnetic field is produced around a current carrying conductor, as we saw previously. The magnetic field is produced around the current carrying conductor within a certain pattern, and we explored this when we were looking at higher physics. The field is circular in a cross-section that is cylindrical along the length of the conductor, and we can demonstrate this using the left-hand grip rule. So the arrow here is showing the direction of the current flow. Remember that negative charges. And then we can see that there is a magnetic field around it. If we view this from above, we can see the circular point, the red point, is showing our wire, and we've got the magnetic field moving clockwise around it. This follows the left-hand grip rule. So if I give myself a big thumbs up with my left hand, the motion of the electrons is by my thumb, and the fingers show the field lines. You're pointing your thumb up, the field lines are curving around in a clockwise direction. If you change the direction of the current, give yourself a thumbs down, you'll see that the curl of your hand is moving in the anti-clockwise direction. Magnetic field around a conductor. The size of the magnetic field decreases as the distance from the current carrying conductor increases. We see a similar thing with gravitational fields, and we see that with electric fields as well. However, unlike them, this is not an inverse square relationship, it is just an inverse relationship. So we can say the magnetic field strength is directly proportional to 1 over r, or magnetic field strength is inversely proportional to r. We can also show by experimentation that the size of the magnetic field is directly proportional to the current through the current carrying wire. So B is directly proportional to I. We can then take these two things and put them together. So saying B is directly proportional to I over R. You should know by now, when we're looking at directly proportional relationships like this, another way to express them would be, say, a magnetic field strength is equal to a constant multiplied by I over R. In this case, our constant is mu naught over 2 pi. So we end up with the equation B is equal to mu naught over 2 pi multiplied by I over R. This is rearranged, and the form that you see on the relationship sheet is B is equal to mu naught I over 2 pi R. 2 pi R. Think about it. What's 2 pi R? Yep, that's right. 2 pi R is the circumference of the circle, circumference of the magnetic field. So B is equal to mu naught I divided by the circumference. Now mu naught is a constant, and that constant value is 4 pi times 10 to the negative 7 henries per meter, and is known as the permeability of free space. The permeability of free space is found on the datasheet, and it's an important constant in magnetic fields. And actually, you may have come across this a little bit in higher, because we use the permeability of free space and the permeability of free space, epsilon naught, in order to determine the speed of light. So here we have an example from the 2016 paper. A student measures the magnetic induction at a distance r from a long, straight, current-carrying wire using the apparatus shown in figure 14. The following data is obtained. We have the distance from the wire, r meters, we have the size of the magnetic induction in microteslas. Please note, you tend to find that our values of Tesla are very small. So we're going to use micro, we're going to use milli. Please be aware of your scientific notation. We're asked to use the data to calculate the current in the wire. Very, very straightforward. We have the equation as given to us on the relationship sheet. We simply rearrange. You take the value of the permeability of free space from the data at the front of the paper, substitute it in, put in your numbers. Now, what we sometimes find is that people have difficulty rearranging after they've substituted. So what you can do is you can rearrange first and then substitute. We'd only really recommend this within advanced higher, purely and simply because of the number of different variables we have within the equations. You plug in your values, you end up with a current of 2.5 amperes.